In the next problem, we have a graph of f shown consisting of a semicircle and 3 line segments, and g is the function given by g is the integral of f from -3 to x. So g is a function of wherever x ends up to be. For example, this integral always starts at -3, but x could end up at -2, -1, 0, etc. What I've highlighted there is the area from -3 to -2, and there's so much area under that curve. If x instead was -1, then we would have more area under the curve. And I have colored that area blue there to highlight an important thing here. Now, when we move from -3 to -4, we're actually going in the opposite direction. And we would have this integral here, but we always have to go from smaller to larger, or from left to right. And when we do that, we have to change the sign. That means that this function, when I go from -3 to -4, even though that area is above the x-axis, it's going to turn out to be a negative integral there. And from -3 to -5, well, from -3 to -4 is going to be negative, but from -4 to -5 is going to be positive. And we can see that in that case, the area between -3 and -4, -4 and -5 are the same. One is a negative integral, the other is a positive integral, so together they will be 0. So these are some important ideas that will go into play in this particular solution. So if you want to stop and think about that for a minute, I'm going to erase the problem here and then start over again with answering the questions below. Okay. So for part A, we want to find g of 0. And that's just the area under the curve from -3 to 0 of f of x. And that's a trapezoidal area. Remember, a trapezoid has a pair of parallel bases. In this case, the parallel bases are vertical, and the height, which is the perpendicular distance between the parallel bases, is going to be horizontal. So the height here is 3, the distance from -3, and the two bases are 2 and 1. And that gives a value of g of 0 is equal to 9/2. All right, g prime of 0 is going to have to be the derivative of g evaluated at 0. It doesn't mean the derivative of g of 0, but it means the derivative of g evaluated at 0. So we have to find the derivative first. And we can write it with the derivative and the integral function inside the square brackets, and then a bar and little x equals 0 written down at the bottom. This means to find the derivative of g of x and evaluate it when x is equal to 0. Well, we know from the fundamental theorem of calculus part 2 that the derivative of that function is just f of x. We want to evaluate that when x is equal to 0, so that's really just f of 0. So to find that, we go to our graph of f. F of 0 is equal to 1, as we can see on the graph there. So that's part A. G of 0 is 9/2, g prime of 0 is 1. Now next, we want to find all values of x in the open interval from -5 to 4 at which g attains a relative maximum. And we can say that g of x has a relative max when g prime of x changes from positive to negative, when g stops increasing and starts decreasing. And the only place where we know that g prime of x is f of x, and the only place where f of x changes from positive to negative is at x equals 3. So that's part B. In part C, we're asked to find the absolute maximum of g on the closed interval from -5 to 4. We know that the absolute minimum has to occur at either critical values or endpoints. Critical values are where g prime of x is equal to 0. But g prime of x is just f of x. And f of x is 0 when x is -4, 1, and 3. We take those critical values along with the endpoints and we plug them back into the original function g of x. Now we've already determined that at x equals 3 there is a relative maximum, so that can't be the absolute minimum. And for x equals 1, since the function is increasing, since g, the area under the curve, is increasing all the way from -3 to 1, that can't be a relative, it can